In this video, we're going to be solving some introduction to friction problems. A pickup truck is driving, but then a bag of gravel falls from the bed of the truck. Does this make the truck's Fn normal force increase, decrease, or remain unchanged? So, if you can first identify the vertical forces on the truck. We have Fn, and we also have Fg is equal to mg. So if the truck is not accelerating vertically, that means Fn minus mg is equal to 0. Therefore, Fn is equal to mg. What changes? So the change is when gravel falls off. When this happens, total mass is going to decrease. So that means that the weight, which is going to equal to the mass times the gravity, decreases too. That's because Fn is equal to mass times gravity. So therefore, mass decreases. That means weight will decrease. And then normal force will decrease. Does this make the truck's mu increase, decrease, or remain unchanged? Mu is the coefficient of friction. So, what we can do for this question 1, we can also show that Fn initial is equal to the mass of the truck, mass of the gravel, times g. But then after, it's equal to the m of the truck times g. M after is going to be less than the mass before. Therefore, Fn after is going to be less than Fn before. For question 2, coefficient of friction, it depends on type of surface and its material, not on the mass. Therefore, the friction is going to be unchanged. Does this make the value for friction acting between the force and the road increase, decrease, or remain unchanged? So the formula for friction force is the coefficient of friction mu times the normal force. This has no units. Fn is measured in newtons. Therefore, Ff is going to be measured in newtons. So if mu is unchanged and Fn is decreased, that means that Ff is going to decrease. A block is slid across the floor and it slides a distance d before stopping. If the mass of the block were doubled, would the block slide a distance that is more than, less than, or equal to the distance d? So, for the block that is sliding across the floor, it has a normal force that's upward. It has a weight force equal to Fg equal to the mass times the gravity downwards. And we have Ff that is opposing the motion. It's sliding to, does not say which side it's sliding to, so we're going to say that it's sliding this way. And that would mean that the frictional force is going to be slid this way, Ff, and that's going to equal to mu k times Fn. It always is opposite of the motion, and it's kinetic because it's moving. So Fn is equal to mg here. So if the mass doubles, what happens to the stopping distance? So we know that, again, Ff is equal to mu k Fn. We know here the normal force is going to be mg. So then we can use Newton's second law. Summation of the forces in the horizontal direction is going to equal to the mass times acceleration. Negative mu k times mg, these are the forces that are in the x direction, and that's going to equal to the mass times the acceleration. So we can cancel the mass here. Therefore, we just get that the acceleration is equal to negative mu k times gravity. And we know that gravity is going to equal to 9.8 meters per second squared. Therefore, A is going to equal to meters per second in the unit. And our mass cancels, which is why we got that. Now we can also use kinematics for this. We know that the stopping condition is going to be v squared is equal to v initial squared plus 2 times the acceleration times the change in your displacement. We know that vf is going to equal to 0. So therefore, that's equal to 0. Now we just have that 0 is equal to v initial squared plus 2 times our acceleration. And we have our acceleration over here is this value. So we can plug that in here. This is going to be negative mu k g times our d, which is our displacement. Now after this, we can multiply that. That's going to be the initial squared minus 2 mu k g d. D is going to equal to v initial squared divided by 2 mu k g. There's no mass in this equation. Therefore, it's independent of mass. Therefore, the distance stays the same. If the initial velocity of the block were doubled but the mass is unchanged, how much would this affect the distance the block slides before it stops? We can refer to kinematics equations. So we have that our initial velocity is going to double. What that means is that we can compare the original to the new. Originally, we have d is equal to v initial squared divided by 2 times mu k g. Now we have that 2 times the velocity initial squared is equal to 4 times the initial velocity squared. And our new distance is going to be equal to 4 times the velocity initial squared divided by 2 times mu k times g. This is going to equal to 4 times d if we compare it here. Because we can see that d is this, and this is just d, and that is just scaling it by 4. Therefore, we can see that distance becomes 4 times larger. Suppose you press a book against a vertical wall with your hand so that the book does not move. Draw a free body diagram and identify the forces involved. For friction, think about which way the book would slide if you were not pressing hard enough. Now, the book is pressed vertically against the wall. We have Fg equals mg, which is going to be acting down. We have the push force, which you're going to apply. That's against the wall. And we have the normal force that is going to be away from the wall. You can actually draw this way. Fn is going to be pointing against the surface, is going to be perpendicular to our axis. Now we can compare the magnitudes. When the book is not moving, in this case scenario, we know that in the x direction, In the y direction, we're going to have forces. Here, we're going to have the F push will be equal to, let's call this F push, is equal to Fn. They're going to be equal magnitude. But when in the vertical direction, we're going to have F is equal to the mass times the gravity. Gravity is going to be accelerating it downwards, and upwards there's going to be a frictional force, F. And actually this frictional force is going to be equal in magnitude since it's not moving. Now for our FBD, upwards we have the friction, downward we have gravity, and then horizontally we have our push and our normal. Now, if you decrease your push but the book still did not move, how would the following be affected? Identify whether each increases, decreases, or remains unchanged. So we know that if the push decreases, that means that Fn has to decrease. Right now they are, right now they are equal in the horizontal direction. And since we know that Ff is going to be less than or equal to the static friction mu times the normal force, that means that if Fn decreases, that means that Ff max decreases too. But right now, book is not moving. So that means that Ff is equal to mass times gravity. So we also know that gravity is going to be unchanged. So finally, we can write that Fn is going to decrease. Our push force is going to decrease. Our gravity force is going to be unchanged. And our Ff is going to be unchanged. If you decrease your push so that the book accelerates down, how are these affected now? If the book is accelerating down, it's going to slide down too. So that means that the friction becomes kinetic. It's no longer static because it's no longer keeping the book there. It has already been overcome, and now it's going to just be slowing the motion, the rate at which it slides down. It's going to be doing negative work. So we have that in our vertical forces, we have downwards our mg, and we have upwards our ff equals to mu k Fn. And since it's accelerating down, we know that mg is going to be greater than ff because mg points down. So it has to be overtaking in the downward direction in order to pull the book down. So therefore, if we draw the FBD again, if we drew the FBD again, we have our downward is going to be larger. We wrote that there. Our downward is going to be larger, and for our horizontal, we have our push, which is equal to our normal, and they're both going to decrease though. Overall, we can write that Fg is the only one that's going to be unchanged because gravity never changes, but the rest of them, they're all going to decrease. A sled slides across a horizontal surface. If the sled slows down to friction with an acceleration of negative 0.67 meters per second squared, what is the value of the coefficient of friction? So we know that the acceleration is going to be negative 0.67 meters per second squared, and we want the coefficient of friction. So on the sled, it is on a horizontal surface. So we can draw this box of the sled, and we have our normal force that is acting up, and we have our Fg that is acting down. We also have our Ff that is going to be opposing the motion. It's sliding, but it doesn't say which direction, so we're just going to write that it's going to be sliding in this direction. And that means that our frictional force is going to be opposing the motion, so it's going to be this way, Ff. There is no vertical acceleration because it's only going in the horizontal direction, sliding to the right. Therefore, Ax is not going to equal to 0, but Fy is going to equal to 0 because Ay is equal to 0. There's no vertical acceleration. Fn, we can write the Newton's law. If Fn is pointing up, mg is pointing down, that's equal to 0. Therefore, Fn is equal to mg. Now, those are going to be equal length arrows. Now, we can do our horizontal. We know that f of x is equal to ma, and we know that it does not equal to 0. So we can write that we have negative ff. The only force is going to be our friction right now, and that's going to equal to the mass times the acceleration. It's actually slowing down, so we don't have to write f slide. So we only have ma. So you have ff is equal to negative ma dividing both sides by negative 1. Ff, we know that ff is equal to mu k times fn, and it's kinetic because it's moving and it's just sliding down. Now this is going to equal to negative ma. We know that fn is equal to mg, so we can replace that is equal to negative ma. And we can see we have mass in both sides, so we can cancel out the mass. Therefore, we have that mu k times g is equal to negative a. Mu k is going to equal to negative a over g. So if we plug in our values, then we have that mu k is going to be equal to negative 0.67 meters per second squared divided by 9.8 meters per second squared. And we have meters per second squared over meters per second squared. That's going to equal to 1. So that cancels out. And we just have here a negative times a negative. That's going to be positive. We have 0.67 over 9.8, which is going to give us a coefficient of static friction, of kinetic friction, of 0.068. And this is a unitless quantity. The coefficient of friction acting between a 1,200 kilogram car and the ground is mu is equal to 0.15. The car is towed to the right with a massless rope. Ft is equal to 3,640 newtons. What is the acceleration of the car? Given that our mass was just 1,200 kilograms, our mu was 0.15, and our Ft was equal to 3,640 newtons, we can first draw the FPD. On our FPD, the car is on the ground, so we can draw, this is our car. We have our normal force that is acting up, and we have our mg that is acting down, and they're going to be equal in magnitude since the forces in the vertical direction is going to equal to 0 because there is no acceleration in the vertical direction. So in the horizontal direction, we have a tension force that is pulling the car to the right, and we also have a frictional force that is to the left. We have to determine which one is larger because we need to know what the acceleration of the car is. So we're going to leave that ambiguous for right now. So Fn, we know, is equal to mass times the gravity because we know that in the vertical direction we have Fn in the positive direction, and you know that you have mg in the negative direction. So that was Fn minus mg is equal to 0. Now over here, we can substitute in 1,200 kilograms times 9.8 meters per second squared, and you have 11,760 newtons. For our frictional force, you have Ff is equal to mu times Fn. And you know your mu you were given was 0.15. Your normal force that we just calculated was 11,760 newtons. That's going to equal to 1,764 newtons. Now, in order to find our net force, Fnet is going to be in our horizontal direction. Fnet in our x direction, that's going to equal to the summation of the forces. So that's going to equal to Ft minus Ff. Our tension force is going to be given to us, it was given to us as 3,640 newtons. And our frictional force that we calculated was 1,764 newtons. So that's going to be 1,876 newtons. And since we know that 1,876, so now we can compare. So we have Ff was 1,764 and Ft was 3,640. Our right arrow is going to be larger. So that means that Fn, yes. And we can find our acceleration now. So acceleration is equal to Fnet divided by the m. That's going to be 1,876 newtons divided by 1,200 kilograms. Our units, newtons, that's going to be kilograms. Right now we have kilograms times meters over seconds squared. And we have that over meters per second squared. So what we do is we cancel out this is actually kilograms. Yeah. So we just have meters per second squared. Our acceleration is going to equal to 1.56 meters per second squared to the right. That means that Ft is larger than Ff. An object's flat surface slides across the ground. You know that mu k is 0.26 and mu s is 0.35. What force is needed to start a 45 kilogram object moving on a horizontal surface? So we were given that the mass is 45 kilograms. Mu k is 0.26. Mu s is 0.35. In order to find the force to start motion, our maximum static friction is equal to mu s times Fn. Our normal force is equal to mg. And mg is equal to 45 kilograms times 9.8 meters per second squared, giving us 441 newtons. Now Fs max is going to equal to 0.35 times 441 newtons equal to 154 newtons. That's approximately going to be rounding down 150 newtons. What force is needed to keep the object moving at a constant velocity? Constant velocity means that your acceleration, your change in your velocity over time, is equal to 0. That means that your applied force has to equal to your kinetic friction. And that happens when we set Fk equal to mu k times your normal force. Now we know mu k was 0.26 and our normal force was 441 newtons, which we calculated earlier. So that's going to equal to 114.7 newtons, approximately 110 newtons. If the object is pushed with a force of 210 newtons, what is its acceleration? We know that net force is going to equal to 210 minus 114.7. That's going to equal to 95.3 newtons. So our acceleration is equal to 95.3 divided by 45. That's going to equal to 2.12 meters per second squared. A box is pushed with a 92 Newton force to the right, but it doesn't move. What friction force acts on the box and why? Our push was equal to 92 newtons to the right, and the box does not move. So that means that Fs, static friction, adjusts to match applied force. Therefore, Ff is equal to negative 92 newtons. This is a Newton's third law, equal but opposite reaction. So these are going to be this is an action reaction pair. So that's equal magnitude, opposite direction. A 9.2 kilogram table is pulled across a horizontal floor using a rope that is angled 21 degrees above a horizontal. If the rope was pulled with a force of 84 newtons, what is the magnitude of the normal force? This mass is going to be the table. This is going to be the floor. It's pulled across a horizontal 21 degrees above the that will be 84 newtons, 9.2 kilograms. Now, we want the magnitude of the normal force. We know that Fg is going to be equal to this. Now, we know the mass, 9.2 kilograms. Force was 84 newtons. Theta is 21 degrees. Normal force, you have to break this into components. So in the horizontal direction, you have Fx, which is F cosine of theta. In the vertical direction, you have Fy, which is equal to F sine of theta. And we can write these. So Fx and Fy. Fx is going to be equal to a value, and Fy is going to be 84 sine 21 degrees. We need Fy. We actually need Fy because it's going to be in the vertical direction, so we don't need to compute Fx. That would be 84 cosine 21 degrees though. So Fy is going to be 30.1 newtons. Now, if we look at the vertical forces, we know that the summation of the vertical forces is going to equal to 0 because the vertical acceleration is going to equal to 0. So that means that you can write that Fn, which is in the positive direction, plus Fy, which is also in the positive direction, minus the mass times the gravity, which is your force of gravity, aka your weight acting down, is going to equal to 0. So that means that if you solve for Fn, you have that it's equal to the mass times the gravity minus the vertical Fy component. So to compute your weight, mg, that's going to be 9.2 times 9.8, which is going to equal to 90.16 newtons. Now, if you sub that back in, that's going to equal to 90.16 minus 30.1, which we found earlier. That's equal to 60.06 newtons, approximately 60 newtons up. What is the magnitude of the horizontal pulling force? Well, up here, we can also write that mg is greater than Fy. So we know that the downward angle is going to be, that downward arrow is going to be larger. because it has the Fy to help it, and those have to balance out. So now we can compute the horizontal component in order to find the horizontal pulling force, because we're looking at the horizontal now. So Fx, which we were computing earlier, is going to be equal to 78.3 newtons to the right. Now we have to find our frictional force. Our frictional force is going to be opposing our motion, which is Ff, and that is going to be equal to mu k times your normal force, which is 0.50 times 60.06, which is equal to 30.0 newtons. Here.